cipher was one of the first substitution ciphers made. A substitution cipher is where you substitute each letter of the alphabet for a different letter. In the @bash cipher, the first letter of the alphabet is equal to the last. The second is equal to the second to last, and the third is equal to the third to last, and so on. So in English, this would be A equals Z, B equals Y, C equals X, and so on. The name of the cipher, in fact, describes the cipher itself. It tells how the letters are interchanged. In Hebrew, the same thing would be Aleph, A, equals Tav, Z. Bet, B, equals Shin, Y. The sounds of these letters are A, Ta, Ba, and Ch, which spells @bash, which is why we call this cipher @bash. However, most historians believe that this cipher was not made for encoding secret messages, because if you knew how it worked, you can decode it very easily. The skytail cipher was first used by the Spartans in Greece. A transposition cipher, which is the type of cipher this was, is where you have the letters of the message scrambled up in a certain pattern. In the skytail cipher, you would take a strip of paper and wrap it around a stick called a skytail. Then you would write your message with one letter in each strip. Then you would unwind it, and the cipher would only be decodable by winding it around a matching skytail. The Caesar cipher, an additive cipher, is one of the most simplest kinds of substitution ciphers. In the Caesar cipher, each letter of the alphabet is encrypted as the letter N letters after the first letter. For example, with a shift of N equals 4, the letter A is encrypted as the letter E, because E is 4 letters ahead of A in the alphabet. And for the same reason, T is encrypted as X. So our message AT will be encrypted as EX. The Caesar cipher is relatively easy to break. It involves frequency analysis. And this was discovered by an Arab mathematician, Abu Yusuf Yaqub ibn Ishaq al-Kindi, al-Kindi for short. Al-Kindi realized that one way to solve an encrypted message, if we know its language, is to find a different plaintext of the same language, long enough to fill one sheet or so, and then count the occurrences of each letter. We call the most frequently occurring letter the first, the next most occurring letter the second, the following most occurring letter the third, and so on until we account for all the different letters in the plaintext sample. Then we look at the ciphertext we want to solve, and we also classify its symbols. We find the most occurring symbol and change it into the form of the first letter of the plaintext sample. The next most common symbol is changed to the form of the second letter, and so on, until we account for all the symbols of the cryptogram we want to solve. The Vigenère cipher was actually invented by Giovan Battista Beasso, although people think it was Blaise de Vigenère who was the actual inventor of the cipher, since it's named after him. This cipher is made of different Caesar cipher shifts. The amount of shifts depends on the keyword length. You choose a keyword and then write the keyword repeatedly above the plaintext message. In our example, we have the keyword dog. every plaintext letter under the keyword D needs to be encrypted with your Caesar cipher shift of n equals 3. Because then, ciphertext D will be equal to plaintext A. In the same way, every plaintext letter under O will be encrypted with your Caesar cipher shift of 14, and every letter under G will be encrypted with a Caesar shift of 6. If there are 4 letters in the keyword, there will be 4 wheels instead of 3. Mary was the Queen of Scotland and cousin of Elizabeth I. She led a very unfortunate life in Scotland and was forced to flee to England. She thought she would be safe under her good cousin's protection. But she was wrong. Elizabeth put Mary in a guarded place that became a furnished jail for Mary. Many historians think this happened because Elizabeth was a Protestant while Mary was a devout Catholic. Some Catholics who resented Elizabeth decided to become Mary's supporters. They sent a coded message to Mary, telling her that they would get Mary out of jail so that she could take over the throne of England. Mary wanted to escape the place badly, so she agreed. But the code Mary used was not strong enough, and Elizabeth's subjects cracked it. Now that they had broken Mary's code, they did have proof, and showed it to Elizabeth I, who ordered Mary immediately executed on charge of treason to the Queen. The code that Mary used was a nomenclator. There was one symbol for each letter, symbols that stood for commonly used words, a few different symbols that were nulls, these were used to confuse the code breaker, and one doublet that meant the letter after it was to be said twice. Thomas J. Beale, with 29 other workers, discovered and mined a large quantity of gold and silver in a place north of Santa Fe, New Mexico. Beale buried it for safekeeping near Bedford, Virginia. He thought that he might not be able to return to claim his treasure, so he entrusted a locked iron box to his friend, Robert Morris. He told Morris to open it if he did not return in 10 years. 23 years passed with no sign of Beale. Morris opened the box. There's a letter from Beale in plain English and 3 pages of encrypted numbers. The letter told how the treasure was found and explained that page 1 told where the treasure was hidden, page 2 described the treasure, and page 3 lists the people who would share the treasure. Only the second page was deciphered. People are unsure whether these ciphers are a hoax or real. Samuel Morse invented a code made up of high-pitched dots, short sounds, and dashes, long sounds. Each letter was a combination of dots and dashes. So, if you wanted to send a message, you would write each letter with the short and long sounds that are assigned to it. 1 dash is equal to the length of 3 dots in quick succession. Space between the letters is equal to 1 dash, and the space between the words is equal to 7 dots. Friedrich Gaskiski broke the Vigenère cipher using the knowledge of strings. He reasoned, what if there is a group of letters in the plaintext that occurs in the same order more than once, and the same letter of the keyword are above this group of letters? Then the ciphertext will be repeated twice. Then Gaskiski counted the number of letters from the beginning of the first repetition to the beginning of the second repetition. He wrote down all the factors of the distance. Then he repeated the process with a different group of letters that repeated and wrote down its distance factors. Then he would continue this process until there are no more repeating strings left. Then the common factor of all the distances are possible options for the key length. Once you have figured out the key length, you number every letter. Suppose the key length is 3. You number the letters 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. Then you group all the letters under each number together. You perform frequency analysis on each group of letters. You then decrypt it like a combination of Caesar cipher. Arthur Zimmermann, Germany's foreign minister, sent a telegram to Mexico convincing it to fight with the U.S. This way, the U.S. would be too involved at home to enter World War I. But the British cryptographers decoded it and showed it to President Woodrow Wilson, who immediately asked Congress to declare war on Germany. During World War II, the Germans used a complicated machine that encoded using a cipher called the Enigma cipher. This machine looked a bit like a typewriter, but it had wheels and wires that worked together in a complicated yet systematic way. The skill of the Polish and British codebreakers helped the Enigma to be cracked early on in the war without the Germans knowing that the British knew how to crack the Enigma. The computation used to crack the Enigma was helpful in building the world's first electronic computer, the Colossus, which was built around World War II. In World War II, Navajo Indian code talkers played a very important role. A group of Navajos developed a code based on the Navajo language. They used words like ant and apple in the Navajo language to stand for A, badger and bear to stand for B, and so on. Without the Navajo code talkers, the outcome of the Pacific battles of World War II would have been very different. The Navajo code is probably one of the only codes that nobody has ever been able to crack. Until the 1970s, there was always the fundamental problem in cryptography of how to keep keys secret. In 1976, Whitfield Diffel, an enthusiastic cryptologist, teamed up with Stanford University professor Martin Hellman and came up with an idea that eliminated the need to keep keys secret. In all ciphers, the decryption key and encryption key are almost the same. If you know the encryption key, you'd know the decryption key too. In Caesar cipher shifted 4, to encrypt you add 4, and to decrypt you subtract 4. So the encryption and decryption variables are the same. Diffie wondered if there could be a cipher where the decryption key was different from the encryption key. In 1977, NASA paid $10 million to Ronald Rivest, Adi Shamil, and Leonard Altman to come up with the RSA cipher, which is still in use today. In RSA, the user chooses his own encryption key and decryption key. He keeps his decryption key secret, but puts his encryption key in a public key directory so that anyone can send him encrypted messages. But nobody can decrypt him except he. When you want to send a private email message, your computer automatically encrypts the message using RSA and the encryption key of the receiver of the email to encrypt your message. When the receiver gets your encrypted message, his computer decrypts the RSA message using his RSA decryption key. NASA had paid Ronald Rivest, Adi Shamir, and Leonard Adleman $10 million to come up with a system that was supposedly foolproof. But in 2013, 7 years ago, a trio of researchers, namely Danilil Genkin, Adi Shamir, who was also the co-inventor of RSA, and Iran Tromer, showed the world that it was possible to crack RSA using just a few emails plus a microphone that was inside a smartphone sitting on a desk. Here's how it worked. Suppose Dan wants to send private emails to his friend Jess, but Jess's sister Becky wants to read the emails too. Since Dan is sending a private message, his computer encodes the message using RSA. But Becky hacks into the computer system and uses what is known as a side channel attack. Now both Becky and Jess's computers will receive the encrypted message. Jess's computer will automatically decrypt it. Becky, on the other hand, would meet a locked box, but using newly discovered information and a microphone on Becky's smartphone, Becky can listen to the tiny high-pitched sounds made by Jess's computer when decoding it, so she can use that information to decode the message herself. I decided to put together a pie chart of, during different time periods, the amount of ciphers invented.